last speaker for the day is Viet Tran. Is that roughly pronounced correctly? Yes. What is the correct pronouncement?
Viet.
It's
a Vietnamese name, yes.
So the T you don't really pronounce, Viet T.
T? Well, yes. My real second name is T, and
T
is family name.
I see. Okay, so he will talk to us about random walks on simplicial complexes, and we'll learn what has to do with epidemics during his talk.
Thank you very much. So I'm really sorry about that, but my talk will, of course, it's motivated by epidemics, but you will not see very much epidemics during this talk. So it's a work that we did in collaboration with Laurent de Creusefond, who is at Institut Mines Télécom, Paris, Thomas Bonis, who is a professor in Université Gustave Eiffel, where I work, and Zihan Zhang, who was a former PhD student of Laurent. So first I will show some motivations, but let's recall some basic. Now I think that everybody knows these notations. So we will consider static non-oriented random graphs, and also after simplicial complexes. And the graph will have, let's say, small n vertices, and edges will be non-oriented pairs. But after that, we will sometimes also consider oriented pair, UV, with U the starting of the edge, and V the alter of the edge, the direction toward which the edge is directed. Adjacency matrix will be G. Of course, you know GUV is equal to 1 if you have an edge between the vertices U and V. And you can also define the degree of U by looking at the line GUV. So let me give, sorry.
Is it 0 or 1 or could be different?
Sorry?
GUV. Is it only 0 or 1? Or?
Yes, it's only 0 or 1. So my motivation was the following. So I had a former work with colleagues where we studied contact tracing for HIV epidemics in Cuba. And as you see, for instance, this was the large component of the data that we had. So it's a very large component, and you don't see many things. And one of the questions that we were wondering was asked this morning by Yegane. It was what kind of models do we put on graphs? Because depending on the network model, we have different processes for describing how the epidemic spread on this model, on this network. And unfortunately, when we have real data and we look into it, none of the simple mathematical models that we have fit the data. So you can see that you have a lot of correlations between vertices. But what we did is that to try to understand more the structure which is on the left, we did a clustering. So here it's a modularity clustering, but we could have done also spectral clustering. And the clustering, it helps you to find groups of vertices which are more strongly connected to the other, and few connections between the clusters. And once we did that, so the left graph becomes the right graph. And in the right graph, what you can see is that, well, you have colors. The colors, they indicate, for instance, the one for HIV, one important variable is sexual orientation of individuals. So the red ones were more heterosexually composed, and the green ones were more like men having sex with men. And what you can see is that you have a stratifications of colors. All the red ones are on the same side, the green one on the other side. And we could link also this to the age of epidemics. Red clusters are older clusters, and we have a propagation in time. So epidemics was introduced in Cuba by people coming from military mission in other countries. And then it spread in the countries and jumped to from military men to women, and then to men having sex with men. So you have a history that you can obtain. So the history also explains why simple network structure doesn't match the data. And what we see is that we have some big clusters, and when we try to see if the big cluster can correspond to simple mathematical models, sometimes they do. So, for instance, in many big clusters, I try to infer the degree distribution, and then to see whether we can consider that vertices were connected at random or not. And sometimes it was the case, sometimes it was not the case, but so my conclusion was that, okay, maybe we can do simple models on some cluster and then try to assemble all the bricks. But still, I had a remaining question, which was, is it possible to have a more clear information on the topology of the network? Because this is something that is really important for epidemiology. And when we deal about clustering, so it refers to connectivity. So let me recall two basic definitions. So you have the Laplacian of the graph, which is the adjacency matrix minus the matrix with the degrees in the diagonal. So let me draw a very simple example. I have one triangle here, let's say 1, 2, 3, and one separate edge, 4 and 5. So I recall things that everybody knows. So if I write the adjacency matrix, so 1 is connected to 2 and 3. So we have something like this. 2 is connected to 1 and 3, and 3 is connected to 1 and 2. And here you have only zeros because 4 and 5, they are separate. And we have something like this. Okay, so this is adjacency matrix G. I subtract to it the degree distribution, so -2, -2, -2 on the first block, and on the second block, -1, -1. Okay. In fact, it's easy to see that the kernel of this matrix is of dimension 2. Okay, you can find very easily the 2 eigenvectors that span the kernel of this Laplacian matrix. So, of course, you have 1, 1, 1. And the second one is you have first block 0 and second block 1. So what you see is that the kernel of the Laplacian matrix, one basis that generates this kernel, is done by indicators of the vertices which are in the same connected component. And what is important? So this is about connectivity. It's related also to clustering and kernels. It's related to the spectral properties of the Laplacian matrix here. And we know also that the Laplacian matrix, if you see it as an operator, as I showed here, it's also the generator of the random walk that works on the graph. It's a walk which starts from a vertex, let's say 1. It chooses one of the neighbors at random. So with probability 1/2, it jumps to 2, and with probability 1/2, it jumps to 3, etc. Okay. So in fact, this is the discrete time random walk, but we can also look at a random walk that waits an exponential time, let's say, of mean 1, and after this exponential time, chooses one neighbor to go to. Oh, sorry. Each neighbor calls the vertex with at rate 1 after an exponential time, and the first one to call is the one that is visited. Okay, so in a second project that we had is also related to visiting these networks by random walkers. So when you deal with sexually transmitted disease, for instance, or with Marie-Geoffrey Rousside and co-authors, we also look at people injecting drugs. These things are sometimes people don't want to reveal their true contacts or even their true nature, whether they are heterosexual or homosexual. And Of course, you cannot do a database saying this person takes drugs and has how many contacts and here are the names. So one thing is to explore complex network. We can just let random walker explore them, and this is called a snowball sampling or respondent-driven sampling methods. All these things are related. And
so what are these three-letter acronyms? What is ACV?
HCV is a hepatitis C virus.
And RDS?
RDS is respondent-driven sampling.
Okay. Oh, S is really something?
Sampling.
Sampling. Oh, I see.
Sampling. The idea is just that people don't want to reveal their real name, but you can give them like a coupon, a small ticket. And for instance, if you want, you can give each individual 3 tickets. He gives them to his or her contact. And these contacts come and take also an interview. And so you can reconstruct the graph. You know exactly who knows whom without having the names of people coming, for instance. This is a rough idea. And our question was, can we design, can we think of other way to explore unknown network by spreading other kinds of workers on it? Okay. For instance, if we let random worker go, we see that we will have somehow the Laplacian operator or a modification of it, and we will recover information on the connectivity or at least clusters, etc. But there are also other things that we want to obtain. For instance, if you have a very specific structure that is here a circle, this is not indicated by the Laplacian matrix. Okay, but from the topological point of view, the number of connected components is what is called the Betti number beta 0, and you have also topological indicator, other Betti numbers, which are beta 1, beta 2, that indicates the number of holes, for instance, like this, or cavities, if you look in higher dimension, etc. So if you have just one graph, of course, you can complexify it by saying, for instance, here, so this is data from Australian. I forgot to mention them orally. It's David Rawls and co-authors. And as you can see, sometimes you have cliques. So when you have 3 vertices connecting together, you can add a triangle to your graph. If you have a clique of order 4, you can add a tetrahedron, etc. So you can generate in this way a higher dimensional structure. And now the question is, can we explore this higher dimensional structure with random walkers, and what is the information that is given? And the second thing is also that for me, when I discovered the topic, so it's not published yet, but it's maybe soon, but it's something that we started several years ago. It's just that sometimes life is very slow. And when I discovered these structures, as a probabilist, I wanted some probabilistic explanation of the Betti numbers or some topological quantities. And so I try here to explain from a probabilistic way all these notions that arise from topology and geometry. So let me recall what is a simplicial complex. So we can look at a simplex. So a simplex is just a set of a k-simplex is a set of k plus 1 vertices. So you can say a 0 simplex is just 1 vertex. If you look at 1 simplex, you have 2 vertices, so it's an edge. Okay. So what we do with graph is one-dimensional. Now, if you have a triangle, so this is 3 vertices, so this is 2 simplex. Okay, because triangle is in 2 dimensions, and if you have a tetrahedron, so it's a 3 simplex, etc. Okay, you can go. You have 2 orientations for the simplices. So we will denote them by plus or minus. Okay. So when you have a triangle, in fact, the orientation of the triangle it gives an orientation on edges. And if I take the other orientation, I will have the other orientation on edges. And we call the face of a k-simplex the k-1 simplices that are obtained by taking out one vertex. So for instance, if I have a triangle, the faces are the edges of this triangle. And the co-faces is a reverse. So for instance, the co-face of this edge are all the triangles that admit this edge as face. And the simplicial complex is a sum of all these objects of different dimensions. So vertices, edges, triangles, tetrahedron, etc. And the only constraint that we have on simplicial complex is that when we deconstruct it, we should have all the elements in the simplicial complex. That means that if I have a k+1 simplex in my simplicial complex, all the faces should be also in C. I say it with other words. If I have a triangle, the edge of the triangle should be also in the simplicial complex, as well as the vertices of the triangles. Okay, you want something a bit hierarchical, so that when you deconstruct it, all the elements are also here. And so so the simplicial complex is denoted by C. So in the sequel, I will use one example to illustrate what we say. So simplicial complex C is like a graph. You don't need to have all the edges. Okay, some are here, some are not here. It's a collection that satisfies only that if you look at faces, they are here, provided the higher structure is here. So let's say we have 1, 2, 3, 4, 5. And so these are the edges. You see, of course, that some edges are missing on my picture. And I add also these two triangles. And you see, for instance, that the edge 3, 5 is not on my picture. And so this is my simplicial complex C. And for a given C, I can look at all the simplex, the k-simplex of this simplicial complex. So for instance, if I look at S2 of C, it's all the triangles of my simplicial complex. Here I have only 2. I have, let's say, 1, 2, 3. And I have also 2, 3, 6. Is it clear?
The simplicial complex is itself a graph?
It's more than a graph. It's you add also triangles, tetrahedron, etc. If I look at S1 of C, it's a set of edges. And if I look at the pair S0 of C, S1 of C, this is a graph. Okay. If I add S2 of C, I have a graph plus triangles, etc. Yes, exactly. She said the
hypergraphs are special.
Yes. Okay.
A hypergraph is not a simplexizer.
No, because you don't need to have these hierarchical inclusions, but it's close as well.
So what is special that you're doing simplicial complex? I could have more general cell complexes. I could have 4 cycles and the facet making the 4 cycle, maybe some cubes. And so you could have very general cell complexes. Why are you only looking at things which are generated by triangles, tetrahedrons, and so on?
Because we could do what you say. It's possible. Here's the only thing is that I want to have a, you see, if I go further, I have tetrahedrons. This is 4 vertices. So if you do like this, for every number of vertices, you have the corresponding click. If you do like a cube and then 4 cubes, so for some k, you have no corresponding structure. That's the only reason why we do, but it would be possible. From an informatic point of view, I suspect that it could have even more. Well, I'm not sure of that. I discuss this later. So let me give example of simplicial complexes that interest us. So the Czech complex, sometimes to model the fact that you have correlations between vertices, you can, and this is something that we will do later, you can try to put them into a latent space where they have positions. And if they are close, they are more likely to have edges. And what you can do is that you can take some distance r, positive, and you say that if you have k plus 1 vertices for which all the balls intersect, then you add the k-simplex that corresponds. So for instance, if you have two balls that intersect, you are sure you have an edge. If you have a third ball that intersects the intersection of the two previous balls, you have the triangles, etc.
So this is, if you vary R, this gives you persistent homology, right?
Exactly. But here we don't do that. This structure is complicated because you see you have some conditions that involves balls. So the geometry has a very important role here. But the Rips-Vittoris complex is the same, but more easy to do. So what you do is that instead of looking at the intersection of all the balls, you say that if you have all the edges, then you add the higher dimensional structure. So what I said before, so when you have a graph, you add the cliques. So this corresponds to Rips-Vittoris. So you can have, for instance, 3 individuals connected, you add the triangles. If you have a fourth one that connects to the 3 previous one, you add the tetrahedron, whether the balls intersect or not. And later, because things are very complicated, what we will do is we will also resume to a triangulation of the torus, and we'll see what we can do with that. So when we have, now we need a bit of algebraic formalism. So we will call a chain. It will be the span of simplices, k-simplices. Okay. For instance, it's here the sum of all the tau, let's say, k-simplices with positive orientations, and I put real number or complex number, let's say real, in front of it. Why do I do that? So it seems a bit strange at first, but at some point, I want to describe also path in my graph. So imagine I want to have this path 2, 3, and 3, 4. I can say that this is a chain, which is 2, 3 plus 3, 4. Okay, I can do things like that. And what happens is that imagine that here I continue my path. It's like this, and it can turn several times and use several times the same edge. So I want sometimes to put before an edge a weight that is more than 1, maybe 2 or 3, depending on whether the path uses several times a given edge. Okay. It will become more clear in the sequel, I hope. So when you do this, you have a vector space. If the original structure is finite dimensional, so you don't have any difficulty in defining this. You can define also the norm that corresponds. If you have n vertices, this is like a finite dimensional vector space. So you have the usual norm that say that the square of the norm is the sum of coefficients to the square. Okay. So this is a Hilbert structure, and you can define the dual. So the dual are linear functions, but here because everything is finite dimensional, you can even identify the dual CK with the K above with the space of chain, the CK with the K below. Okay. In any case, they are isomorphic. So.
You didn't tell us that do you have duals in your complexes? So do you, if you fix a dimension, you would consider the center of a tetrahedron dual to it? And
no, it's not the dual in this respect, it's really an algebraic dual. For instance, if I look at edge, let's say vertices, okay, the dual will be generated by the function u star, such that u star v is equal to 1 if v equals u star equals u or 0 otherwise. And you can do the same for, but it's not a kind of dual graph or dual thing. It's really algebraic dual here. Okay. So we have a boundary map. So boundary map, it takes a k-simplex, and it does this kind of so it goes from ck to ck minus 1. So it takes a k-simplex and it gives you a k minus 1 chain, which is defined like this. So you subtract the vertex I and put in the chain a weight minus 1 to the power I. So by definition, we can say that if k equals 0, delta 0 is 0. It's a null application. And we can check that delta k, so delta k plus 1, it goes from k plus 1 simplices to k simplices, and then to k simplices to k minus 1 simplices. And what we see is that if we compose these two ones, they are 0. So let me give a very simple example. I take a triangle, 1, 2, 3. So if I look at delta 2 of this triangle, okay, I take out the first vertex. So it's minus. So I take out the first vertex 1. So it's minus 2, 3. Then I take the second. So it's plus, sorry. Then I take, so this is vertex 0. I take out vertex 1. So it's minus 1, 3. Yes, exactly. And then I take out the vertex 3, and it's plus 1, 2. And then I apply delta 1 on top of this. So it's a linear application. Okay. What you can see is that delta 1 of 2, 3 is 3 minus 2. Well, 3 the vertices. I mean. Okay. Minus here 3 minus 1, and then plus vertex 2 minus vertex 1. So it's a chain, it's a linear combination of vertices. And what you see is that each one, the 2 appears once with minus and once with plus. So everything simplifies. See, I have minus and minus, so it's plus. So everything simplifies, and in the end, it's 0. Okay. So this is something that is well known in homology. So they say that the image of delta k plus 1 is included into the kernel of delta k. And they have this k homology vector space, which is the kernel of delta k quotiented by image of delta k plus 1. Okay. So it seems very strange for us, but in fact, we have a probabilistic interpretation of this. So that's what we will, I will show just now. And the dimension of HK, the k homology space, is beta k. So from topology, you know that beta k is the number of cavities of dimension k, but we would like to understand a bit more where this comes from. So let's take, for instance, k equals 0. Okay. So for k equals 0, look again. So it's a kernel of delta 0. Delta 0 is a null application. So the kernel of delta 0 is all the vertices, V. And then you look at image of delta 1. Image of delta 1, when you take an edge UV, by delta 1, you have V minus U. So the image of delta 1 is the span of all the chains U minus V with U and V edges of my simplicial complex. And you can say, okay, I take all my vertices and I put an equivalence relation that says that if I have a path between these two vertices, they are in the same component. So I can understand that beta 0 is a number of connected components. And we want to do the same for beta 1, beta 2, etc. So that's what we will do. So, that's important. Okay, so let me talk just before doing the probabilistic interpretation. Let us consider co-boundary applications. So we know how to go from k-simplex to k-1 simplex, but you can do the reverse as well. So you take a function that acts on k-1 simplex, and you want to define the co-boundary that acts on k-simplex. Okay. The way of doing is, so this is, we didn't invent this, it already existed before, but the co-boundary application, it acts on F by saying that if you look at the image of some k-simplex, F acts on k plus, F acts on k-1 simplices, so you have to take out one vertex, and you look at the image of F on this k-1 simplex, and you combine all this with the -1 to the power I, depending on who you have taken out. Okay, and because these are F are linear functions here, so everything is linear, you can see that delta k star of F is also F applied to delta k of the k simplex. So you have a kind of duality relation where you can invert. Later on, we will have like scalar products, and you can use this as adjoint operators. So let us give just an example to understand this co-boundary map. If you look at delta 1 star of F applied to the edge V0, V1, it is F of V1 minus F of V0. So you can understand it as a flow, okay? Especially if you take F to be U star, the function that is equal 1 when you take the vertex U and 0 otherwise, what you see is that if you look at delta 1 star of U star of the edge UV, you have -1 because U is the vertex from which you live, And if you look at delta 1 star U star of VU, it's 1 because here U is the vertex at which you arrive, okay? And otherwise it's 0. So delta 1 star, you can interpret it as a kind of flow in what follows. Okay. So at this point we have a kind of people in topology that like this very much, all these kind of diagrams. So you have all the space CK. I just write them so that we can keep this in mind later. So you have the boundary applications that maps CK plus 1 into CK. CK and CK plus 1, CK, sorry, they can be identified with a dual. Okay, here's the same. And you have the co-boundary maps that goes in the reverse direction, and that applies to a function acting on k simplices, and gives you a function that applies on k plus 1 simplices. Okay, so. And so now you can define a kind of a higher order Laplacian. So they are defined like this. So the combinatorial Laplacian is given by the sum of two operators. The first one, so you start from k simplices, you go to k minus 1 simplices. Sorry, you start from k plus 1 simplices, you go to k simplices, and then you go back to k plus 1 simplices. So you start from ck plus 1, sorry, I did a mistake. Okay. You apply first, of course, you apply always first the right one. So you apply delta star k plus 1. So you start from ck, you go higher in dimension. That's why you have an arrow to the an upward arrow. And then when you are in the higher dimension, you apply the boundary maps that takes you back to CK. And for the lower Laplacian, downward Laplacian, you first go from CK to CK minus 1 by applying the boundary map. And then you take the co-boundary map that maps you again to k-simplices. Okay, what are the, and there's a combinatorial Hodge theorem from the topology that says that if you look at CK, the space of chains made of k-dimensional simplex. So it's the image of delta k plus 1 plus the image of delta k star plus the kernel of the combinatorial Laplacian. And because you look at the dimension, beta was the dimension of hk, in fact, you can show that hk is has the same dimension as the kernel here. And beta is also the dimension of the kernel of this Laplacian. Okay. You can now forget everything that are on these two lines. What I wanted just to use is that these operators Lk, in the same way as in the spectral clustering, we look at the kernel of the Laplacian matrix. Now we are looking at the kernel of these combinatorial Laplacians. Okay, let me give an example to understand this a bit better. Look at L0. So L0 is, for L0, it's simple because you have the downward Laplacian, which is 0, because it's composed with delta 0, so it's 0. So you have just the upward Laplacian, delta 1 star. So G is no longer here the adjacency matrix, but G is the matrix of the boundary map. Do you see if I write here, or maybe you don't see very much? So if I look at the boundary map, I have, for instance, my vertices, 2, 3, etc. And here I have my edges, 1, 2, 3. I try to do the same matrix in case I'm lost after that, but I can list all the edges. Okay. Here one is appears in 1, 2. I will take a -1 because it's the ego of the vertex, of the oriented vertex. And in 3, 1, I take a 1 because it's the vertex to which I go. Okay. If I look at 1, 2, here 2 is a vertex to which I arrive. So I have 1 like this, and then I have only zeros. And for 2, 3 is the same. Here I have -1, and here I will have 1, etc. So I have a matrix like this. And if you look from a matrix representation of this formula, so you have L0 is G times G transpose. So what happens when I look at for instance, the line 3 and the column 2? So the only time where the line, so column 2 is also the line 2 here of G. Column 2 of G transpose is the line 2 of G. So the only time when you have both entries that are non-zero is when you have the edge 2, 3 or 3, 2. Okay, and then the product is -1. And when you have when you are on the diagonal, so if I look at 1, 1, in fact, whatever I have -1 or 1, when I do the product, it's +1. So on the diagonal, I will have the degree of the vertex. Okay. So when you look at how you can write L0, so you see that you have minus. So for U star, it's a minus. Yes, it's -1 when V is different from U, and it's the degree. So in fact, I should maybe have I have a minus, yes, that I didn't saw, but you saw it from your place. So it's minus the sum of V star. So this corresponds to this -1. plus degree of u times u star. Okay. And what you can see is that this can be interpreted as delta 1 of uv. Okay. The thing here is that I just wanted to show that by taking, here I apply the operator L0 to u star. You can also apply L0 to other function f. Maybe I can skip the computation. And what you see is that minus L0 is the generator of the random walk that goes from u to v at rate 1 when u and v are linked by an edge. Okay. Yes.
When your cochain, your coefficients comes from real number R.
Yes.
Was there special?
No, yeah.
In your definition of cochain, your coefficients,
Yes.
lambda v comes from the real numbers. Is there any reason why you take it? Because you could have taken any ring or field if you want, right? In your definition of cochain.
Yes, we wanted to.
What is the advantage of having
Yes,
R?
my function is just a function that takes some, let's say, vertices
Yeah, sure,
or cases.
Sure. But in your definition of cochain, I could have taken the coefficients lambda not coming from R, but maybe just F2.
Yes, yes.
Or any ring, or
Yes,
is there any
that's true.
advantage?
That's true. And one possibility is to take, for instance, z over 2z. So it's always 0 or 1.
Yes, yes.
Yes.
F2, yeah.
Yes.
Exactly. So what is the advantage than having
F2.
R?
And we took R because that was what we did. But yes, other possibilities are possible as well.
Because it's more combinatorial, right? 0, 1 is there.
Yes, after that, we want to take the limit when you have a large graph. And that's maybe, but taking F2 would have been easier. So
Thanks.
Sorry.
Sorry, I'm a little confused about the linearity here. So L0 of UV is the same as L0 of VU, but UV is -1 VU. So L0 is not linear, is that right?
Sorry, tell me again.
So L0 of UV is -1.
Yes.
But
And it's also L0 of VU.
VU. So if I swap the two vertices, it's also.
Yes.
So L0 is not a linear operator.
No, sorry. I'm sorry. I think it's not L0 of VU. If you take L0
is just a matrix.
And so there is like a different matrix for different UV.
Yes.
Okay.
No, sorry. This is the coefficient UV of the matrix L0.
Okay, thank you.
Okay.
So it's not L0 acting on the. Okay,
No.
okay.
This is just L0 is a matrix, and sorry, I now understand your question. So this is the entry line U and column V of L0.
Right.
So and you put all these coefficients, and
Thanks. Sorry.
of course I say also a mistake because I was thinking that I wanted it to be linear, but of course you can take transpose, it gives you the same matrix, so everything is fine. Okay, so in fact what I present here is not new, because there's quite large literature trying to understand the combinatorial Laplacian. So for instance, here I mentioned the main references that we have. So they were Mukherjee and Steenbergen and Parzanchevsky, Rosenthal, but maybe I missed other authors. But in this paper, they try to give probabilistic interpretation as well of the combinatorial Laplacian. And it's a bit difficult because I have shown you only the good part, the upward Laplacian. And the upward Laplacian has the feature of the generator of a random walk. So I have shown here for L0, but you can do it for the other one. If you look at the downward Laplacian, it's not so clear. So for instance, Mukherjee and Steenbergen, if I don't mix the two references, they need to have random walk with death or branching. So it's not so easy, and you can interpret also the both operators separately, but then you have to merge them together. So it's always a non-trivial thing. So what we did here is that we try to propose another random walk, and we don't want to deal with, well, if we are interested in the spectrum, what we can show is that the spectrum of the two operators are the same. So for that, we need only to interest ourselves in the upward Laplacian. Okay. So we try to find a random walk for which the generator is the upward Laplacian, and that stays in the kernel of the downward Laplacian, so that if it stays in the kernel of the downward Laplacian, this term will disappear. Okay, so what is the kernel of the downward Laplacian? It's if you look at the triangle, if you look at a chain, for instance, a sequence of edges for which there is no boundary vertex, okay, the Laplacian will be 0. So what we do is that we will consider the random walk on the space of chains. The space of chains is the kernel of the boundary application delta k. So for instance, if you look at k equals 2, you have a surface without holes on it. But if you look at k equals 1, what we have is that we have a path for which the starting point and the ending points are the same. Okay, and what we will do is that we have a chain valued Markov chain in continuous time, and each time we want, we will, for instance, here there is a triangle. I take this triangle and I can add a triangle and have a new path in this way. Okay, so I have a chain valued, a cycle valued, imagine k equals 1. I have a cycle valued Markov chain, and it explores the simplicial complex by using the triangles as a way to go. So to make things more precise, just look at the usual random walk. Usual random walk, this is the generator of the usual random walk. You go from x to y when you have an edge between x and y. Then y, in terms of chains, you can also write that it is x minus the boundary of the edge xy. Okay, and what is this boundary of edge xy? It is the image of delta 1. So you see that in the homological space that we had just before, the kernel of delta k quotiented by the image of delta k plus 1. In fact, the kernel is a space in which we take our values, and the image is gives us the transition of our Markov chain. Okay, so this homological writing with quotients is very natural if we think of state space and transition of the Markov chain. So if we go to the chains, so the kernels of delta 1 are all the cycles, and the transitions are given by triangles. So if I take one triangle, the boundary of the triangles, it gives me the 3 edges. Because I take minus, so I subtract the edges that was common to the cycle, and I add instead the 2 new edges. We can show a lot of things. So we can show that, of course, the generator is Lk, but because we are in the kernel of L downwards, so Lk upwards for these cycles are the same as Lk downwards. It's a strong Markov chain. Maybe I should think to the xt remains in the same homologic class as x0 by construction, because you visit only if you start in an equivalence class, you cannot jump to the other equivalence class. And that's why we can think of it as the spectral clustering, where when you are in some component of the kernel, you stay in the same connected component and you don't jump to the other one. We have some difficulties, except if we take like the coefficient in F2, as you say, because even in the triangulation that I showed before, let me do this quickly. things can become very degenerate. So we took triangulations. We could do that on the whole space, but we do this on the torus to have things compact for later purposes. And what can happen is that you have a path like this, then it goes down, and because it's a torus, it comes from the other side again, and nothing prevents it to merge again. And here you have this path which is used twice. And in fact, you can loop like this, and you can have a path that is used an infinite number of times when you want. Okay, so it's like you have a chain, and suddenly you do a lot of loops like this, and then you go out. These things make that it's a bit tricky sometimes, especially for later purpose when we want to rescale this kind of random walks. If you have a kind of things like this, it's very degenerate. So showing tightness, for instance, is not so easy. But when we have a finite number of k+1 simplices, provided we start in let's say with a chain cycle with a finite number of edges, okay, we can show that this Markov chain is it's ergodic and it has a unique invariant measure pi. And for this, in fact, what we prove is that we have we show what is called already Lyapunov. Well, we have a very simple Lyapunov function, which is the norm, and we have this kind of inequalities that are very famous in main and 3D work, for instance, and that ensure that this is a Lyapunov function. You have a negative coefficient in front of it, so you cannot go to infinity. Well, you cannot escape, and it gives that the Markov chain has unique invariant measure. Okay, maybe I can. Is that clear, or maybe I was a bit too fast? I can maybe skip this and discuss this with those interested just after. As I say, so this is the proof of the inequality I was just showing. It's a then Zihan in her thesis, she tried to use these walkers to have statistical simulations, but also statistical applications. So what she did is, for instance, she simulated networks with holes, and what she discovers is that the unique invariant measure, when she looked at it, it discovers the boundary of the holes. So it's not exactly the random Markov chain that we have. She did a kind of simulated annihilating using this Markov chain to have this, but she can show this kind of things. And to conclude, I just want to say some words. Naturally, that when you have a Markov chain, there are two things that you want to do. First is to try to see what is its behavior in long time. Does it has an invariant measure, etc. And second thing is to renormalize and rescale this random walk to see if you have a continuum limit, because sometimes things are very complicated on discrete structures and they become more simple when you have continuum. To have continuum, you cannot stay in a very abstract space. So that's why we look at geometric graphs. I just say this as a teaser. So we can, if we have a geometric graph, it means that our vertices, they have a geometric position, let's say in the torus, for instance. And then we rescale the random walk. So it's not so easy. We can look at convergence of generators. Convergence of generators is okay. It's not simple, but it's something which has been studied a lot, especially in informatics or machine learning literature. You have a lot of convergence of different generators. To have tightness, etc., is a bit more complicated, but I just want to conclude with this. So we can show convergence to an operator which is called the Laplace-Beltrami or Hodge operator. And this is a kind of limiting object that we want to have. So you see, you have the cycle. The cycle is not necessarily just one loop, because what can happen is that your cycle can break into two cycles. Okay, if you have one cycle, and then you have a bottleneck, and then you subtract the triangle of the bottleneck. So then your cycle can become two bubbles. Of course, these two bubbles, they can merge again, and as long as I say it's the same homology class, but if this is the case by construction. So in the limiting object, you can have several connected components, and what we would like is to understand a bit more this kind of images that we have. But this is a bit far from epidemiology. That's more from our mathematical perspective. And if I conclude in one sentence with epidemiological purposes again, one thing that I would like to do, but it's not at all but for contact tracing, you know, it's like we have been exploring the graph by asking for the neighbors. And for what we did in France, for instance, well, not me, but what people did in France is that the social workers, they go and try each contact one by one, like randomly, without any other methods than just there is a list and we have to ask all people of the list. And imagine that for some epidemics, you want to go fast, for instance, if the people give you 10 contacts, well, you have no other means than just either asking the whole 10 contacts or saying, okay, I take 3 or 4 at random. But if the people say, I know A and B, but I know that A and B also are friends. So this gives you a triangle. So my idea was if we have a bit more information, but this is not completely absurd. Like, you know, if your friends know each other or not, this is something that you usually know. So if you give this extra information, and if you do contact tracing by using a higher dimensional structure, do you go faster in discovering the shape of the network and the places where the illness can propagate or not? So this is a kind of question. Well, thank you very much.
Thank you very much. Questions?
Thanks for your talk. I had a question about, there was a point where I think it was towards the end, so you went through it quickly, but you said we find the identity of these holes, we find the boundary of the holes.
Yes.
Is this related to, so I guess, can you provide intuition on how you do that? Is it related to like the k-chains that are in the kernel of this Hodge?
Yes, so she starts with cycles at random and she let them move. And after that, she looks at, there's an invariant measure. So she can look at edges, how many times they have been occupied by the chain. So of course, if you are far from the holes, you maybe visit once or twice, but the chain spends more time on the hole because it's like reflected on them. So that's how she can find this in the end, that these edges have different roles.
But the chain can also have non-zero support away from the holes, right?
Yes, yes.
So I guess she averages over several.
Yes, because if she, it's a good point that you raise. Your chain, it stays in a connected component. So for instance, if the chain is around this, for instance, you start from this red chain here, you can never discover the second one, okay? You have to start another chain around this hole to find this hole.
You could have two chains that are kind of not just around the hole, but have support, overlapping support in the regions that are not around the hole.
That could have been. I admit I have not looked in detail in her coding because she was a PhD student of my collaborator, but I can, if you ask me, I can give you precisions after.
Okay, thank you.
More questions? No?
I had a question, but go ahead. You're closer.
Whoever gets it has to carry it around.
Oh, see, that was maybe not an optimization. So my question, so thank you. This was really interesting, Viet. So a question that I have is, do you have sense about how quickly do these chains converge? I mean, if you do this random walk, how quickly can you get to the stationary distribution?
Yes. So when you have the when you have this kind of identity here, you can also have exponential convergence rate, but because we are here in Berkeley, so some people will tell you that this exponential convergence rate is not true, and you might have a cutoff. But I'm not familiar with this. I haven't looked into this kind of stuff.
Okay, so you don't know what's sort of the size of lambda m here, right? What's
well, in fact, this is a theoretical, so you should know that it should at least converge exponentially fast. But if you want the lambda m, you should know the matrix LK. And in applications, sometimes you don't know the whole.
No, I thought maybe you run an example. You know,
no, I don't. I didn't investigate this.
Okay. All right. Thank you.
So I don't know anything about this stuff. It was an excellent talk. I really enjoyed it. My questions are kind of about the last slide when you kind of talked about how you could use this for epidemics and the Laplace Beltrami part. So I kind of, if you wanted to do something like spectral clustering, but using this, right? So I guess, first of all, what does that result that you derived based on the convergence to that up? Does it tell you about what kind of data you need for it to be embeddable well? Like, is it, like in the original case for spectral clustering, you know that it should have some kind of manifold setup?
Yes.
Yeah.
Well, I'm not sure that the rescaling would be useful for clustering. Okay. But indeed, the idea is that, for instance, for some data, you might the graph might converge, for instance, to a manifold, as you say, and for instance, here's the torus because it's a triangulation of the torus, and then the Markov chain converges to a diffusion on this manifold, for which you have also tools to study it. But for the use of this for clustering, I don't know if it gives any result or not. I haven't thought about it.
Okay, more questions? Well, let me ask the follow-up question on this. Is there sort of, so in general, if we had a random walk on some graph and it converges to some manifold, we would expect it converges to some kind of Brownian motion or so on that manifold. What would be the analog of this higher dimensional Brownian motions? How should I think of them?
Yes, so it's, well, the simulation is this image here, and so it's we have the generator of this process. So on linear functionals, like let's say, so linear functionals is now the path is like continuous path, and linear functional is integrals of differential forms along this path. So for this, the generator corresponds exactly to the Laplacian L upward, which is in differential form given by this. So when you apply to a function phi, you have something that combines the derivatives. But then, is it like some loop process studied by some people or related to other?
Yes,
I
that was
have
my
no clues
question.
about that. I don't know. I suspect there might be some, but for the moment, I
Okay. Okay, well, I think we deserved some party. So we have our welcoming party, which is from 4 to 5. I'll see you. I think it's outside. I'm not sure. Actually, I will see. It's either, I think it will probably be just out here.
Yeah, I could. I did.